In this video tutorial, we're going to be carrying out some calculations involving steam cycles, and in particular we're going to be looking at the ideal Rankine cycle. At the top of the screen there we have a schematic diagram of our Rankine cycle, or the plant involved in our Rankine cycle. We have a pump which feeds a boiler. The superheated steam exiting the boiler is then expanded through a turbine, and then we condense the steam back to water. We also have a temperature entropy diagram to represent that cycle. So position 1 is the entrance to the pump. We increase the pressure of the water, and we have water entering the boiler. The water is then heated until it reaches the saturated liquid point, here on the temperature entropy diagram. And we continue heating that water until it changes state from wet saturated vapour to dry saturated vapour at this point here. If we continue to apply heat to that steam, we're going to eventually end up with superheated steam at position 3. So in the boiler, we heat the water, we evaporate the water until it becomes steam, and then we superheat that steam. Positions 3 to 4 then is the expansion of the steam through the turbine, and we can see that what we have there is an isentropic process. The reason we know it's an isentropic process is because if we take an index mark here, on our entropy axis, we can see that that entropy corresponds with both position 3 and position 4. So we have isentropic expansion through the turbine. Then from positions 4 to positions 1, we're condensing the steam until it becomes wet saturated vapour, or saturated water over here at position 1, before we enter the pump, where once again we have an isentropic process. So we increase the pressure of the water at constant entropy once again. Now directly underneath the diagrams we have a descriptive question, and as we go through this descriptive question we're going to extract the relevant information, but we're also going to relate this to our temperature entropy diagram. So the first thing that we're told then is that our steam power plant operates on the Rankine cycle, and we're told that we have a boiler pressure of 20 bar and a condenser pressure of 0.5 bar. Now, we know from the previous tutorials that the processes in the boiler and in the condenser are constant pressure processes. So if we refer to our temperature entropy diagram then, we know that the entrance to our boiler is position 2 and the exit is position 3. So we can write P2 equals P3 because we have a constant pressure process, and we know that our boiler pressure is 20 bar. We also know that the pressure at the entrance to the condenser, position 4, and the pressure at the exit of the condenser, position 1, is equal. So we can write P4 equals P1, and we're also given that pressure for the condenser, 0.5 bar. So we already have some information about the pressures at each of those positions. The question goes on to read, the steam exiting the boiler is superheated at a pressure of 20 bar and a temperature of 550 degrees C. So we've already noted that the pressure at position 3 is 20 bar, but we now also know that the temperature at position 3 is 550 degrees C. The question reiterates there that we have superheated steam, which we know anyway because position 3 sits in the superheated region on the right-hand side of our temperature entropy diagram. The question goes on to say it undergoes isentropic or constant entropy expansion in the turbine until the condenser pressure of 0.5 bar is reached. So once again it's emphasising that the pressure at position 4 is 0.5 bar. And we've already made a note of that. Okay, so the steam exiting the turbine is fully condensed. Well, once again we know it's fully condensed because as we go from position 4 to position 1, position 1 sits on the wet saturated vapour line, so we know we have saturated water at position 1. So the steam exiting the turbine is fully condensed and enters the pump as saturated water at 0.5 bar. Once again we're confirming P1 is 0.5 bar and we have saturated water at position 1. It then reads the water exiting the pump has a pressure of 20 bar and an enthalpy of 342.5. Well, we already knew that position 2 had a pressure of 20 bar, but we have some additional information here. we're actually given the enthalpy at position 2. So because we have water at position 2, we're being given the enthalpy. So 342.5 kilojoules per kilogram. Next, we're given the mass flow rate of 0.85 kilograms per second. And in the final sentence there, we're told what parameters we need to determine. So it says determine the enthalpy of the steam throughout the cycle. Well, we already know H2, but we need H1, we need H3, and we need H4. So we need to determine those enthalpies. We also need to determine the rate of energy transfer at each stage and the thermal efficiency of the steam plant. Well, we're not able to determine the rate of energy transfer or the thermal efficiency until we have each of those enthalpy values. So we're going to focus on finding the 3 missing enthalpy values first of all. Okay, so taking each of these in sequence, the first enthalpy that we're going to find is the enthalpy at position 1 on our temperature entropy diagram. And at position 1, we know we have wet saturated vapour, so HF. And we also know the pressure at position 1 is 0.5 bar. So to find H1, we need to look up the value of HF at 0.5 bar. So if we go over to our steam tables, so here we have the steam tables for saturated steam, and what we're looking at here is the first page of the steam tables that you've been provided with, but we notice here that the left-hand column, or the reference column, is temperatures. Now we haven't been given temperatures in this instance, we have been given pressures, so we scroll past the first page. The second page is a continuation where temperature is the reference. And when we come to the third page, our reference is pressure in bar. Now we have a pressure of 0.5 bar, and we're looking up the HF value that corresponds with 0.5 bar. So if we go along the top, we have a column here for saturated liquid, HF, and where that row and column meet, we have our enthalpy value of 340.5. Therefore, H1 is 340.5. So making a note then of enthalpy 1, we have 340.5 kilojoules per kilogram. The next enthalpy value we're going to find is for H3, which is superheated steam. We have a temperature of 550 degrees at position 3, and we have a pressure of 20 bar. So this time we need to go to the superheated steam tables at 20 bar and 550 degrees C, and we need to get our enthalpy value. Now, whilst we're there, we're also going to get our entropy value, S3, because we need to use the entropy at position 3 in order to determine the entropy at position 4, and hence the dryness fraction of that steam. So whilst we're at the steam tables, for 20 bar and 550 degrees C, we're going to look up the enthalpy and entropy values at that temperature and pressure. So returning to the steam tables, the page that we're on here is for saturated steam, but we're looking for superheated steam. So if we scroll on to the next page, here we have superheated steam, but what we're looking for is our reference pressure of 20 bar. The first table here covers 0.06 bar and 0.35 bar. We then have 0.7 bar and 1 bar, 1.5 and 3, and so on. So we continue moving through these tables until we get to our pressure of 20 bar. We were also given a temperature of 550 degrees. So we're using the left-hand table, and our reference values sit on the same row as our temperature of 550 degrees C. Well, panning along that column then, we can see that we have an enthalpy of 3578, and we can see that we have an entropy of 7.570. So let's take those values back across, and then we can find the remaining enthalpy for state 4. So H3 then was 3578 kilojoules per kilogram, and the entropy at that state was 7.570. The units there are kilojoules per kilogram Kelvin. Now, because we know the expansion of the steam is isentropic or constant entropy, we know that that also equals the entropy at position 4, or S4. So moving to the right-hand side then, what do we know about position 4? Well, we know the entropy at position 4 is 7.570 kilojoules per kilogram Kelvin. We know that the pressure at position 4 is 0.5 bar. And we also know that we have wet vapour, because here at position 4, we're somewhere in between dry saturated vapour on this line here and wet saturated vapour on this line here. We can see that that steam has a dryness fraction which is closer to 1 than 0. The dryness fraction of dry steam is 1 and the dryness fraction of wet steam is 0. So we need to determine the dryness fraction of that steam. Well, the way that we do that is by looking up SF at the reference pressure of 0.5 bar, and we also need to look up SG at the reference pressure of 0.5 bar. We know that our entropy of 7.570 is going to sit somewhere between SF and SG, and we need to determine where it sits between those values because that's going to give us our dryness fraction X. So let's get our two entropy values and then we can determine the dryness fraction. So first of all, we need to return to the tables at the top which represent saturated vapour, or saturated steam in this case, and we need the table where pressure is the reference. We already have highlighted 0.5 bar, but this time we're looking for the entropy values. We have an entropy value 1.091 for saturated liquid and 7.594 for saturated vapour. SF then is 1.091, SG is 7.594. So we have 7.594 and 1.091. The units for both of those are kilojoules per kilogram Kelvin. And what we can see now is that our value of 7.570 sits between the SF and SG values, but it's much closer to the 7.594 or the SG value. Therefore, we know we're going to have a very high dryness fraction. The way that we determine our dryness fraction then is using the following formula. S equals SF plus X SG minus SF. We saw that equation in the previous video. And rearranging that to make X the subject, we need to subtract SF from each side and then divide each side by SG minus SF. That gives us X equals S minus SF divided by SG minus SF. Now, the other thing we know here is that we're trying to determine the dryness fraction at position 4. Therefore, this value of S needs to be for position 4. We have all of our numbers here. We have 7.570 minus 1.091 for SF divided by 7.594 minus 1.091, giving us a dryness fraction for our steam at position 4 equal to 0.9963 to 4 decimal places. I'm just going to make a note over on the left-hand side here. So we have X4 equals 0.9963. And dryness fraction is dimensionless, so we don't need to add any units there. Okay, let's clear some space and then we can determine H4. So the formula that links enthalpy and dryness fraction is as follows. H equals HF plus X Hg minus HF. This time we're looking to determine the enthalpy at position 4, so we use our dryness fraction at position 4. Now, as we said previously, our pressure at position 4 is 0.5 bar. And we already have HF at 0.5 bar. Over here for H1, we said HF at 0.5 bar was 340.5 kilojoules per kilogram. So we have HF, but we need to look up Hg at our reference pressure of 0.5 bar. So returning to our steam tables for the last time, we already have highlighted our pressure of 0.5 bar, and we can see we already have highlighted HF of 340.5. The remaining enthalpy value then, Hg, is 2646. Okay, so Hg equals 2646 kilojoules per kilogram. And so now we can calculate H4. We have HF, 340.5. We have a dryness fraction at position 4 of 0.9963. We have an Hg value of 2646. And we have an HF value of 340.5. Giving us an H4 value then equal to 2637.47 kilojoules per kilogram. So I'm going to make a note of our enthalpy value H4 over on the left hand side, and then I'm going to clear some space so that we can carry out our final calculations to determine the rate of energy transfer at each stage within our cycle. Then finally we can determine the thermal efficiency of our steam cycle. Okay, so the first process in our cycle is P in, or the power input by the pump. The power input is the mass flow rate times the change in enthalpy across the pump. Well, at the exit of the pump we have H2, and at the entrance we have H1. Our mass flow rate is 0.85. H2 is 342.5. And H1 is 340.5. Giving us a value of P in at the pump equal to 1.7 kilowatts. Now we know that the units there are kilowatts because each of our enthalpy values are already given in kilojoules per kilogram. So the values in the table are in kilojoules per kilogram, therefore each of our energy transfers here are going to be in kilowatts. Once we exit the pump, we enter the boiler. So we have phi in at the boiler, the rate of heat energy transferred into the steam. Once again, it's the mass flow rate, H3 minus H2 this time, because position 3 is at the exit of the boiler and position 2 is at the entrance. 0.85, H3, 3578, H2, 342.5. Giving us a phi in value equal to 2750.18 kilowatts. Once we exit the boiler, we enter the turbine, and this is where the steam does work on the system, or we expand the steam in order to generate mechanical power. So we have P out at the turbine. Now note that this value is going to be negative because the steam's doing work on the turbine. Therefore, energy is leaving the process as we create mechanical work. So we expect this to be negative. But we have mass flow rate. The exit of the turbine is H4 and the entry is H3. 0.85. H4, 2637.47. H3, 3578. Giving us a P out value equal to minus 799.45 kilowatts. And finally, we have the energy leaving the steam in the condenser. So phi out, we're cooling the steam or condensing the steam. We have the mass flow rate. At the exit, we have H1, and at the entry, we have H4. So we have 0.85, 340.5 minus 2637 0.47, giving us a thy out value equal to minus 1952.42. Now once again that's kilowatts, and once again it's negative because energy is leaving our working fluid or leaving our steam. When we have a thermodynamic cycle, anytime we're inputting energy, we would expect a positive value, and anytime we're extracting energy or losing energy from the working fluid, we would expect to get a negative value. Okay, so our final calculation then is for the efficiency of this process. And the efficiency of a thermodynamic process is the net power output. Note that it's the net power output there that we're referring to, divided by the rate of heat input. Well, our net power output is the magnitude of our power out minus the magnitude of our power in. Or we can write magnitude of P out minus P in. The reason it's the magnitude of our power out is because we're not interested in the negative sign here. That just tells us that the energy is being lost from the process, but in losing energy from the process, we're putting energy into the turbine, or we're producing power. And dividing by phi in. So let's input some values then. The magnitude of our power output is 799.45, and the magnitude of our power input is 1.7. And the heat input to the process is 2750.18. Now it is worth noting here that our net power output then is 797.75. So the pump here is consuming very little power. Dividing by 2750.18 to get our efficiency gives us an overall efficiency equal to 29.0%. So just to summarise, in this video we were asked to determine the rate of energy transfer at each stage in our Rankine cycle. We were also asked to determine the overall efficiency of the cycle. However, before we were able to determine the rate of energy transfer and the efficiency, we first had to determine our enthalpy values at position 1, 2, 3 and 4. Having determined our enthalpies, we were able to calculate the rate of heat transfer, and we were also able to calculate the overall thermal efficiency of our Rankine cycle. So I hope you found this video useful, and thanks for listening.